Let us practice the theory of implicit function of two variables using the following example. Consider the equation x cubed plus y cubed minus z cubed minus 2xyz minus 2 is equal to 0 and the point 1, 1, 0. So first we denote the left-hand side as a function capital F of x, y, z, which is this expression x cubed plus y cubed minus z cubed minus z minus 2xyz minus 2. First we see that this function is continuous and defined for all triples x, y, z. So this, and as a polynomial it has derivatives of any order. So this is C infinity R3 because it has 3 arguments. Then let's see whether the point is on this set. F at 1, 1, 0 is equal to 1 plus 1 minus 0 minus 0 minus 2 is indeed 0. Well, what set is this? How can we imagine the set of all the solutions of one equation for 3 unknowns? We have x, y, z, 3 independent variables, and we have the condition that this expression is equal to 0. If the expression is linear in x and y, if it were something like 7x minus 5y plus 2z minus 3 is 0, then this is the general equation of a plane. Some kind of surface in a two-dimensional surface in a three-dimensional space. If it contains higher powers or some product or some other functions, then the surface will be no more flat, no more straight plane, it may be curved, but this is still, in a typical case, some two-dimensional surface in a three-dimensional space. And the question is whether we can take a small part of this surface and whether we can look at this surface as a graph of a function small f depending on x and y. So this point does indeed lie on this surface. And now we want the derivative of f with respect to z. 0, 0, minus 3z squared minus 2xy 0. Then we evaluate this derivative at the point 1, 1, 0, and we have 0 minus 2, this is non-zero. That means using these 3 results, f is continuous, the point lies on the surface, and the derivative is non-zero. That means there exists a function relating z and xy. And let's find the first derivatives to be able to write, say, the Taylor polynomial of order 1 or the tangent plane to this surface. So the first derivative can be computed using the partial derivatives of capital F. Here we have with respect to z, and let's compute the derivative with respect to x and y. So we have 3x squared plus 0 minus 0 minus 2 yz partial derivative of f with respect to y, 0, 3y squared, 0, minus 2xz. And when we compute, we evaluate these derivatives at the point 1, 1, 0, we have 3. And again 3. So we can find the partial derivative of f with respect to x as minus capital F with respect to x divided by capital F with respect to z. And when we are interested in the values at this particular point, we can use already these results at the particular point. So this will be minus 3 divided by minus 2, which is 3/2, and fy, which will be minus fy divided by fz, which is minus, and fy is again 3 divided by minus 2, which is again 3/2. So we can write the Taylor polynomial for the 1 for the function small f. We could also write the Taylor polynomial for the function capital F. But this is old stuff. New today is that we are able to write the Taylor polynomial for the implicit function, small f, for which we have no formula. That's new, that's important, that's remarkable. So this is function value, which is the z value, which is 0, plus the derivative with respect to x, which is 3/2, times x minus x0, which is x minus 1, plus f with respect to y, which is again 3/2, times y minus 1. So this is the Taylor polynomial at the point 1, 1 for the function small f. And the Taylor polynomial is actually the equation of the tangent plane. Z is 0 plus 3/2 x minus 1 plus 3/2 y minus 1. Or we can write the normal vector, which will be the gradient of the function capital F, which is fx, which is 3, fy, which is also 3, and fz, which is minus 2. So this is the gradient of capital F, and this gives the normal vector to the graph of this function, which is given by this equation.